Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. So in this subject already we have covered simple stresses and simple shear force bending moment diagrams and the bending stresses so far we have discussed. Today in this session I want to discuss about torsional loads. So due to this torsional loads, torsional shear stress will be obtained. So whenever the members are subjected to torsional loads, so how to calculate that shear stress, the torsional stresses. So we will see, and then we will derive the torsional equation. So the members subjected to torsional loads. So the course outcome is students should be able to analyze the theory of pure torsion. So what is the equation and how to derive this pure torsion formula, and bending to draw shear stress distribution diagrams in circular shafts. Whenever the circular shafts are subjected to torsional loads, how to draw the shear stress diagrams, and then bending moment distribution diagrams in various cross sections of beams for different loading types. The student will learn in this outcome in this module, so that the student should be able to analyze the theory of pure torsion and then calculation of shear stresses. After completion of this topic, they will be familiar. So first of all, we should know the definition of torsion. So whenever the members are subjected to torsional loads, the torsion of circular shafts. So as shown in figure here, the circular shaft is shown. So as per definition, consider a shaft rigidly clamped at one end, the one end is fixed, and twisted at the other end. By torque applying this twisting another end like this, or like this. So applied in the plane perpendicular to the axis of the bar, such a shaft is said to be torsion. See, so there is a shaft axis here. So the applied force, that is F, applied in a plane perpendicular to the axis, then the force multiply with the distance, diameter of the shaft. So we will get torque. The torque is force multiplied with the diameter, or how much from where to here applied the force, the distance. So here, at the same time, you have to calculate the twisting, how much twisted, the twisting angle. So the effects of torsion, whenever the shaft is subjected to torsional load, one is to impart an angular displacement of one end cross section with respect to the other end, to set up shear stresses on any cross section of the bar perpendicular to its axis. So generation of shear stress. So here we will see how to generate the shear stresses in a shaft. The physical understanding of the phenomena of setting up of shear stresses in a shaft subjected to a torsion may be understood from the figure 1 to 3. So here I will show you that 1 to 3 diagrams. So in this, see the figure 1, here the cylindrical member or a shaft, is static equilibrium, where the T is the resultant external torque. The resultant external torque T acting on the member. So let the member be imagined to be cut by some imaginary plane. So that plane is Mn, imaginary plane. So here the cylindrical member or a shaft equilibrium where the T is the resultant external torque. In this diagram shown, the T is the resultant external torque acting on the member. So imagine to be cut by some imaginary plane that is Mn at this on this shaft. In this, in figure 2, when the shaft, so where the plane Mn cuts, remove the portion on right hand side, and we get a figure 2. Now, since the entire member is in equilibrium, so therefore each portion must be in equilibrium. So the member is in equilibrium under the action of resultant external torque T, and developed resisting torque is Tr. See, at this section, so already sectioned here, this Mn plane in previous diagram, they cutted this portion and remove the right hand side portion, and then see the cross section views. So you can see like this, and x and this radius and tau applied at a small elemental area you've taken, that is dA. So the figure shows that how the resisting torque Tr is developed. The resisting torque Tr is produced by virtue of an infinite small shear forces. So acting on the plane perpendicular to the axis of the shaft. So virtue of an, so here infinite small shear force acting on this plane. So the such shear force would be developed by virtue of shear stresses. So therefore, we can say that when a particular member, say shaft in this case, you have taken a shaft, the particular member, it may be round bar, it may be beam, is subjected to a torque, the result would be that on any element, there will be shear stresses acting. So while on other faces, the complementary shear forces come into friction. So thus, we can say that when a member is subjected to a torque, an element of this member will be subjected to a state of pure shear. So now, case here we will see shaft case. The shafts are the mission elements which are used to transmit power in missions. It is a circular cross-section bar. It is a mission element generally used to transmit power from one place to another place. So twisting movement for any section along the bar or shaft is defined to be an algebraic sum of the moments of the applied couples that lie to one side of the section under consideration. So the choice of the side in any case is of course arbitrary. So now suppose, already we have seen in the first case, so this shaft is subjected to twisting moment. So algebraic sum of the moments about the applied couples, one side of the section, suppose you have taken section here, under consideration, the choice of side in any case of course arbitrary. So what is this shearing strain? If a generator A to B is marked on the surface of the unloaded bar, then after the twisting movement has been applied, this line moves to AB. So I will show you here in diagram. So here the AB is the marked generator on the surface of the unloaded bar. So after twisting, the angle G measured in radians. Clear? So actually this is gamma of G. The gamma measured in radians between the final and original positions of the generators is defined as the shearing strain. So how much twisted? So the shear strain as per strain definition. So how much changed due to the particular load? The dimensions of the object. Change in length by original length. Change in diameter by original diameter. So that is a strain. So here the shearing strain is the angular strain. So the original positions of the generators is defined as the shearing strain at the surface of the bar. Previously the generators are A and B marked and then A dash B dash after twisting. The same definition will hold at any interior part of the bar. See here. So this is the angle. So you can refer gamma with R theta. B2, B dash. So here the G is the shear stress by theta. So the modulus of velocity in shear. So the ratio of the shear stress to the shear strain is called modulus of elasticity in shear or modulus of rigidity and then represented by the symbol GRC. So what is this angular twist? If a shaft of length L is subjected to a constant, so the shaft length is L, subjected to a constant twisting moment T along its length, then the angle Q through which one end of the bar will twist relative to the other is known as the angular twist. So that is theta. So despite the differences in the forms of loading, we see that there are a number of similarities between bending and torsion, including, for example, a linear variation of stresses and strain with the position. So here in this case, in torsion, the members are subjected to movements couples in planes normal to their axis. For the purpose of designing a circular shaft to withstand a given torque, we must develop an equation for designing of a circular shaft. So the relation between twisting moment and maximum shear stress produced. So what is the twisting moment T and how much shear stress produced? A quantity representing the size and shape of the cross-sectional area of the shaft. So that relation gives the equation, torsion equation. See, the relationship of torsion is T by J is equal to tau by R is equal to G into theta by L. This is simple torsion theory or development of torsion formula. So in this, the first term refers to applied loading and a property of section which in the instant of the polar second moment of inertia. Second term is, this refers to stress and the stress increases, the distance from the axis increases. First term and second term and third term. The modulus of rigidity and angle of twist, theta and L. So the third term is, it refers to the deformation and contains the terms modulus of rigidity and combined term, that is theta by L, which is equivalent to strain. For the purpose of designing a circular shaft to withstand a load given torque, we must develop an equation giving the relationship between twisting moment, that is maximum shear strain produced, and a quantity representing the size and shape of the cross-sectional area of the shaft. See, in this diagram shown, the uniform circular shaft is subjected to a torque. So whenever they apply torque in clockwise direction and resisting torque acting opposite, the applied shear is shown a small complementary shear. This is a circular shaft with dia D. From this diagram, we will derive simple torsion equation. Refer to the figure shown above, where a uniform circular shaft is subject to a torque. It can be shown that every section of the shaft is subjected to a state of force. Here, the moment of resistance developed by the shear stress being everywhere equal to the magnitude and opposite in sense to the applied torque, already shown here. The applied torque opposite resisting torque acting. So for this purpose, the deriving a simple theory to describe the behavior of shaft subjected to torque, it is necessary to make the following base assumptions. Some assumptions need to require. Based on the assumptions, you have to derive this simple torsion theory or development of torsion formula for a uniform circular shaft designing. So while designing, you should concentrate, you should take all these assumptions. Based on these assumptions, you have to design. The material is homogeneous. That is, the uniform elastic properties existing throughout the material. There is no change of properties, elastic properties. Throughout the section, the properties are same. So that is, the material is homogeneous. The material is elastic. You know, Hooke's law. With shear stress proportional to shear strain. So stress is directly proportional to shear strain. The stress does not exceed the elastic limit. Within the elastic limit only, the stress is directly proportional to strain. Already we know, Hooke's law. E is modulus of elasticity. The circular section remains circular. After twisting also, the circular section is, there is no change in cross section, remains same. The cross section remains plane. The cross section also remains plane whenever this section, after sectioning, the cross section also same. The cross section rotate as if is rigid. That is, every diameter rotates through the same angle. Whenever applying twisting, it rotates. Rotate as if rigid. That is, every diameter rotates through the same angle. Through the same angle. So the rotation angle is theta. So rotation angle is theta. So that the cross section rotates as if rigid. Every diameter rotates through the same angle. So here shown the diagram. Consider now the solid circular shaft or radius R subject to a torque T at one end, other end being fixed. This is a fixed one. Under the action of this torque, a radial line at the free end of the shaft twists through an angle theta. The angle shown here. So point A moves to B. So whenever this rotate, whenever the shaft starts to rotate, A to B. So and AB subtend an angle theta. Sorry, here gamma at the fixed end. This is then the angle of distortion of the shaft. The angle of distortion of the shaft is shown here gamma, that is called as shear strain. So since angle in radius arc upon radius, arc AB is equal to R. Since L and gamma R constitute the arc AB. So now the gamma is R by L from the definition of modulus of rigidity or modulus of velocity in shear. Now, as per definition, shear stress upon shear strain, the modulus of rigidity. See here, the gamma is equal to capital R by radius upon this length. So as per definition, the gamma is the shear stress set up in the radius R, then tau by G is equal to gamma. G is a modulus of rigidity. So now equating the 1 and 2 equation, you will get R theta by L is equal to tau by G. So here already shown here, gamma is equal to R by L. So equating this equation, so you will get R theta by L is equal to tau by G R C. So you can write this equation, tau by R is equal to G theta by L. So here shown where tau dash is the shear stress at any radius R. So now stresses, let us consider a small strip of radius R and thickness dr. Small strip you take here as shown in the figure, the thickness is dr and radius is R, which is subjected to shear stress tau dash. So let us consider a small strip. Already we have taken the radius R and thickness dr. Now calculate force set up on each element, that is stress multiplied with area. So that is shear stress tau dash multiplied with 2 pi R into dr. The strip area, elemental area. This force will produce a moment or torque about the center axis of the shaft, tau dash into 2 pi R into dr into R. So you can write tau dash into 2 pi R square into dr. This is the force set up on each element. Now, the total torque on the section will be the sum of all the contributions. So, since T is the function of r because the torque, it varies with radius. So writing down the torque in terms of equation 1, integral 0 to r 2 pi r square into d tau dash. So now tau dash is equal to g theta by r by L. We get the equation 0 to r, limitations 2 pi into g theta by L into r cube. So now take outside the 2 pi into g theta by L, take outside and integral 0 to r cube dr. So now after integration 2 pi g theta by L multiply with r to the power of 4 by 4 0 to r. So the upper limit is r and the lower limit is 0. So now g theta by L into 2 pi r to the power of 4 by 4, and after simplification you will get g theta by L into 5 r to the power of 4 by 2. So in place of r, you can write in terms of diameter pi d to the power of 4 by 32. So here d by 2. In place of r, you can substitute d by 2. So here 32 g theta by L into pi d to the power by 32 you will get. Since the pi d to the power of 4 by 32 is called as J, that is polar moment of inertia for circular shaft. So now you will get the T by J is equal to g theta by L. So finally T is equal to, after simplification, we got g theta by L into J. So now we can write T by J is equal to g theta by L. So now combine equation 1 and 2. The first one, what is the equation? Tau by r is equal to g theta by L. So now tau by r is equal to g theta by L. Tau by r is equal to g theta by L, and then T by J is equal to g theta by L. Equate these two equations. So where the T is applied external torque, which is constant over length L. J is the polar moment of inertia. So now pi d to the power of 4 by 32 for solid shaft. In the case of solid shaft, there are two diameters already, inner and outer. In case of hollow shaft, so this is inner diameter d and outer diameter capital D. So now you can write the polar moment of inertia for the hollow shaft is pi d to the power of 5 into d to the power 4 minus small d to the power 4 by 32. Polar moment of inertia, where d is outside diameter and capital D is outside diameter and small d is inside diameter. Capital G is modulus of rigidity or modulus of velocity in shear. So theta, here theta, T by J is equal to tau by R is equal to g theta by L. The theta is angle of twist in radians on a length L. Now, the tensional stiffness, how to calculate? The tensional stiffness K is defined as the torque for radius twist. That is T by theta is equal to Gj by L. So already you know this torsion equation already we have derived. T by J is equal to tau by r is equal to g theta by l. This is torsion equation. So from this equation, you can calculate the tensional stiffness. The two terms, the t by theta is equal to gj by l is called tensional stiffness. So how do you calculate the power transmitted by shaft? If torque is applied, if T is the applied torque and the W omega is the angular velocity of the shaft, then the power transmitted by the shaft is, you can calculate by using this relation P is equal to torque applied multiplied with angular velocity. That is equal to 2 pi nt by 60. So here 2 pi nt by 60 into 10 to the cube in kilowatts, where n is RPM. So here the T is the torque. Like this, need to calculate the power transmitted by a shaft. So and tensional stiffness, and torsional equation also we have derived. So these are the references I have taken for this PPT. One is the S. Ramamrutam, the strength of materials, the title of the book, and then the publishers are Dhanapati Rai publisher and R.K. Bansal, a textbook of strength of materials, and R.S. Kurmi, the strength of materials. Title of the book is Strength of Material, and the other is R.S. Kurmi and Gupta, Essan and Co. publishers. Here I have taken this NPTEL sources. NPTEL Harku. The course, the Strength of Material course is available in NPTEL. So these are the references I have taken for this PPT. You can refer any one textbook for more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.